Well, thank you very much. That was a very, very nice introduction. I wasn't aware of that. The textbook is still used. It was quite some time ago, so maybe we need to update it at one point. I have to check whether you can see my screen. So can you see the presentation when I click forward? Okay, good. So I have to thank, of course, a lot of people in geophysics. As you all know, one person cannot do a lot. So these many people from the group here in Fribourg who helped in collecting all this data and also made substantial advances in the theory or in the application. And what I would like to show you today is how geophysical techniques can be used in mountains and permafrost specifically, and why this is so, well, I would say important, by why it's also so interesting from the geophysical point of view, because permafrost, as we will see later, is quite a unique mixture of quite a lot of different materials, and it can be very, very variable. So this is why it's also challenging for geophysics, but of course also very interesting. So there will be some parts about the different ground ice occurrences in mountain permafrost, and then the need to monitor that, also regarding the stability. Now and then, most of my examples will come from basically two case studies or two areas. I would say one is in Europe, let's say our field laboratory in the Alps, in the Swiss Alps, and also all along a gradient in Europe. Mostly using electrical techniques. And then we had quite some applications 5-6 years long in the central Andes, where we used then petrophysical models to quantify ice content, using then also seismic techniques in addition. Now what we're doing in Fribourg is, I guess as many geophysical groups, everything that geophysics can see in what I would say the near subsurface down to around 100 meters. So not the deep geophysics, but everything that is close to the surface, ground ice, water, material composition, anomalies, the bedrock, whatever. And then more specifically, we're heavily involved in monitoring, which is also one of the technical developments, I would say, what we try to achieve with resistivity, electrical resistivity, with seismics, and to combine that with temperature and soil moisture data. Then we're not so much involved in actual developments of instruments, but recently we have a project to build or develop with colleagues in Portugal an autonomous, robust, low-cost ERT system, which can then be placed everywhere by itself to monitor in remote areas. So frozen in our case, but it could be anywhere. We're also involved in development models to quantify the ground ice content, the material composition, and then making evolution models for the future evolution of these different components of the ground. And finally, all this monitoring data has to go somewhere, and at least to my knowledge, is really a big problem in geophysics that there are not so many databases which are public available. So geophysicists are not very good at putting everything together for the use or in a more global sense. So recently we tried to initiate a geoelectrical database only for permafrost, because that's our main expertise, but then worldwide in order to collect then all these data together internationally. Where do we work? As I said, one main region is Europe, for obvious reasons, and there we cover a transect from the Arctic to the Alps, and also recently in Central Asia and in the Andes. There are some dots here which are not ours. It's from this database which we are initiating in resistivity, but we have some measurements in Yukon planned as well. But so far we have done nothing in North America, unfortunately. And the techniques which we use is mainly electrical resistivity tomography, for reasons which I will go into detail in short. Also seismic refractions, radar for glaciers and snow. electromagnetic induction and also recently spectral induced polarization. So the complex resistivity, the phase, and so on. So why do we do this? So, I mean, as I understood, you're also mostly geophysicists, so I don't have to convince you, but I think the main points of geophysics is that it's non-invasive, it's flexible, portable, very important in the mountains that it's portable. And then we have a huge possibility of spatial scales. So we get a spatial resolution as opposed to boreholes where we just get a point information, and we can define our scales from centimeters to kilometers if we want to. So I think these are the big pros. And the main playgrounds, I always call it detecting something, mapping something, monitoring something, and quantifying something. So these 4 parts I will go into a bit more detail. Okay, so much about what we are doing as a general overview. Now, for those of you who are not familiar with permafrost, why is it important and what is it in a nutshell? So it is defined thermally. I could add only thermally. So it's only the temperature must be below 0 for at least 1 or 2 years. Even there, the community is not really decided on whether to say 1 year or 2 years. And it's also, of course, very vague in a way, because if then after 2 years it's again unfrozen for 20 years, was it then permafrost, or was that just a question of temporal scales? In addition, it doesn't say anything about the ice content. It could be dry permafrost without any impact whatsoever. It could be almost pure ice. Then it would not be really considered permafrost, because that would then count as a glacier, which is not permafrost, so to speak of. So this definition makes it already quite difficult to deal with. What is easier is this graph here. So we have the negative temperatures continuously. That would be the permafrost. And in summer, we would have a part of this permafrost, which is thawed, the seasonal thaw layer, which is called active layer. And this is a bit depending, of course, on the atmosphere, but it's also depending on the thermal conductivity of the ground. Bedrock, for example, usually have deeper active layers than if you have coarse-grained material with a much lower thermal conductivity, where the summer heat cannot penetrate as easily as in bedrock. And this is quite indicative for changes in time. So we would expect in a warming climate that this active layer would increase. More and more of the ice which is here will be melted, and the permanently summer thaw layer would increase, which then obviously would have also some issues for stability reasons. So if something is, let's say, has been frozen for the last 1,000 years and now it's thawing, then obviously we don't know exactly directly whether this will cause problems or not. There's also the question of carbon release, as you are certainly well aware of in the Arctic, where we have lots of organic material. So if we increase the active layer, more of the stored carbon, methane or carbon dioxide, which is stored here, can be emitted to the atmosphere. So that's basically why it's so interesting at the moment globally. And that is a sketch of the permafrost distribution, the colors. The dots are measured boreholes. So we see we have quite a good coverage in North America, but not completely, but more in the West. There is in Europe a high coverage in the Alps because it's so densely populated. So the reason to monitor is quite high, and also it's easy to get there. Scandinavia as well, reasonable amount of boreholes in Russia, in Siberia, and also in China. This is only the northern hemisphere. In the southern hemisphere, we have the Andes, which are much less boreholes or much less information from the Andes, although they cover, permafrost-wise, they cover really a large latitudinal gradient. And the present day rate of change due to climate change is shown here on this right-hand side. So the more red or orange, the higher the rate of thawing of the permafrost. So you see for the European perspective, not all over the place, but mostly substantial thawing rates. The same also for Tibet, the same for the more western part of Russia, and for the Arctic as a whole.
Hey, Christian?
Yep.
I don't mean to interrupt. Can you maybe go full screen? I'm getting some comments that it's hard to see some of the text on your slides.
I'm sorry?
I'm getting some comments that it's hard for some people to see the text on your slides. Can you
Okay.
full screen presentation mode?
Is it not full screen?
I think
No,
we're just seeing your PowerPoint as if you were viewing it to edit it, but it might be a
okay.
double screen issue. Yeah.
No, okay. Okay, sorry. Good that you see that. As you say that I'm in screen mode here on my screen, but then I have to just check why is not.
Folks are so excited to get the full content. We interrupted.
Yeah, that's good. Now. I try to close it again and open it again. Stop sharing. Are you still seeing my screen?
No.
No, okay. Okay, let's see. Here we go. No. Do you see it again?
There we go. That looks good.
Yeah. Okay. Sorry for that.
Okay, thank you.
Okay, so now I told you that permafrost is thermally defined. So what does it consist of? So these are examples. The pictures which you see here are examples of what we could call permafrost. That would be a crack in the bedrock, a fracture filled by ice. That would be permafrost. This is a rock glacier where you see an ice rock mixture. So it's not a debris covered glacier. You see this rock ice mixture also below the active layer. This is buried snow here, and this would be ice, so buried snow that has been transferred to ice. Also, this is permafrost. So geophysically speaking, as you can very well imagine, we'll get completely different responses from our geophysical surveys when we are measuring on top of this. So we have a wide range from dry permafrost to ice supersaturated conditions, so almost pure ice, right? So, and as ice content is an important parameter for the stability of rock walls, we actually need to know that. We need to know whether we have this situation or whether we have that situation, right? Now, what we very often have is a part which is clean ice, and then a part where we have embedded rocks. Again, that makes a huge difference for stability. And also geophysically speaking, is now, let's say, a seismic wave, is it propagating through the ice or through the rock, or can we assume a certain mixture model between the two? So then again, that will be different for different geophysical parameters like electrically or elastic parameters. On the other hand, if we talk about soil, which you would find more in the Arctic, then we have interbedded ice in the soil matrix. And if you thaw it, if you just wait long enough in your hand, then you have just mud in it. So then the ice in the pores are melting. So again, a completely different material composition. And the big problem in permafrost studies is, and this is why geophysics are used that often, is that is one of the only components of the cryosphere which is invisible from the surface. So in a glacier, even in a debris-covered glacier, we can see that very clearly from remote sensing, from aerial photographs. Whereas if we go to permafrost, so that is a station in the Swiss Alps on permafrost, with an active layer of around 10 meters nowadays. It has been 5 some years ago. That is frozen below that, but we would not be able to detect that from the surface. The same is, I mean, those are 3 famous mountains in Switzerland, and the rock faces where there is no glacier are also frozen, obviously. So that's also permafrost. Now that's an example of one of these rock falls, debris flows coming from a permafrost area in Switzerland, where debris flow came out of it, killing 9 people and destroying part of a village. They are luckily they are very rare, but they are more frequent now. So this is also why small countries like Switzerland spend so much money on permafrost research, which is good for research, but obviously bad for stability issues in the mountains. That is why also already 20 years ago, European monitoring was started, the so-called PACE project, Permafrost and Climate in Europe. That was a borehole, a series of boreholes along a transect from Svalbard in the north down to Spain, down here. Nowadays, also Iceland is in this network, and the Alps, of course, and Norway and Sweden. And part of that temperature measurements, or almost all of those measurements, are still in place. So that the start was here in 1998, around here. There was one borehole in the Alps which is older than that, but only one. Everything else is younger. So the longest time series, temperature-wise, are around 20 years, usually. We see now warming trends for most of the sites. And we see for those sites who are very close to the freezing point, we see almost no change. So this is again this Schilthorn, which I've shown you before, where freezing, the conditions are directly at the melting point, which means part of the energy is used to melt the ice, which prohibits that the temperature rises above 0 until all of the ice has been molten. So those are the places where people are usually most interested in, because there we expect the largest changes in ice content from ice to water, but we will not see it in the temperature record. And one legacy from this time from these early measurements in Europe was that also geophysical measurements were done at that time in 1998. Those are these dots here. So this is a mean average electrical resistivity of some profiles at permafrost sites all over Europe. And that was it. That was to characterize the site and to decide where the borehole should be, etc. And from this time onwards, there was one site which we tried to continue measuring every year. That was a bit explorative in the beginning, because we were not sure whether by measuring every year we would get a signal which is strong enough, like a thawing signal which is strong enough in terms of electrical resistivity. But it proved to be the case. So this is one of the reasons why I think personally monitoring is a good thing if one has the time to stay to one, to keep measuring at one site. Because now we see actually a decrease in electrical resistivity due to the melting of the ground ice. This trend is now more obvious. So that started at this European PACE project at that time. So nowadays, this is included in the operational permafrost monitoring in Switzerland. So operational means these are the air temperatures in Switzerland. This is borehole temperatures in Switzerland. So in permafrost, so you see it's at 20 meters, much deeper. It's minus, let's say, between minus 0.5 and minus 2.5, but with an increasing trend. But we see also the same trend in this permafrost electrical conductivity. So now it's not resistivity, it's conductivity, because it is easier to compare the curves. And we see that the signal is quite similar, but not identical to temperature. We see, for example, here we have a more continuous increase, whereas we have some fluctuations here, and here we have a stronger dip than, for example, what we can observe, and also a bit earlier than what we can observe here. And this is rock glacier velocity, which is another component which I will not talk about today. So that would be then the temperature evolution and the active layer deepening over time. It's a very extreme example here. Again, this Schilthorn from 4.5 meters in 2000 to almost 12 meters nowadays. Now, what does that mean for geophysical research? So why are we, or what can we do here? Of course, this I have talked already about. More concretely, how much ground ice is there and how does that change runoff and stability? How will it change in near future? And how can we install operational continuous monitoring by geophysical means? Because if we only do it by temperature, we will not know anything about the ice content. As I've said, geophysics is very good at detecting something in a tomogram, an anomaly like this. This would be an ice anomaly in this talus slope. So in between, we have an ice core, which is at 5 meter depth, about 10 meter thick. We can map that in 3D, of course. We can monitor it, as I've shown you. We can just see whether this ice core is changing over time. And we can try to quantify it. So we can try to calculate from these electrical resistivities and, let's say, additional parameters like seismic velocity. We can calculate porosity or ice content, water content in a tomographic, in a two-dimensional way, which is then what all the practitioners are interested in, right? They want to know, okay, until where is the ice going and how much ice do we have? And is it saturated or not? So if the air content is larger than 10% or so, we know we have unsaturated conditions. And then the practitioners have cases like this, an unstable slope here in the Alps. Obviously, we cannot really do a lot here. I mean, we can not monitor here. So we do the monitoring just at the side where there's also a rock glacier, quite similar conditions. And then we can do geophysical profiles like this electrical resistivity, where we have, again, high resistivities. And I will come to that in a minute, why this means ice. And also in this case, a cross profile, which is a bit more, we see much more anomalies here. So the ice content is much more variable, at least that's what we think. And again, I will not go into detail, but of course, we have many more possibilities if we want to look at the geophysical variables of interest, like resistivity, conductivity, like P and S wave velocity, directed properties, wave velocity, etc. Now, why is electrical resistivity so useful? Obviously, air is an isolator, so that should be easily detectable. If we have very high resistivities, we know it could be air. It could also be ice, because ice has also very high electrical resistivity, up to 1 million ohm meters, meaning that in mountain permafrost, where we can have high ice contents, values go from, let's say, around 1 kilo ohm to 1 mega ohm meters here. And water obviously has a much lower resistivity, usually in the mountains between 10 and 100 ohm meters. So huge differences, which are easy to detect. However, ice and air are both isolators, so it could be difficult to detect whether it's really the blocks, the air between the blocks, whether this is air or whether this is ice, whether we have, let's say, an ice-cored moraine or whether we have just a dry moraine. We could have the same electrical signal. And there, the seismic comes into play because the seismic velocities of air, the speed of sound, and of ice, around 3,500 meters per second, are really, I mean, ice has 10 times the velocity of air. So it's very easy to distinguish between the two, and water is in between. So this is why electrical and elastic properties are so useful in a combination for permafrost studies. Obviously, if we're talking then about the geology, it becomes very difficult, and this is where the problems start, right? Because we see also that some earth materials can have very low velocities, very high velocities, and also very low resistivities and very high resistivities. Just a quick repetition for those who are not familiar with electrical resistivity tomography and refraction seismic tomography. Both usually use sensors along a profile line, electrodes or geophones. Both have a source and a battery and a seismic sledgehammer, for example. And both can, from the resulting apparent resistivities, which are measured here, and travel times, which are measured in seismics, both can be inverted into giving tomograms, which then can be tomograms on the same model grid, which we can then combine if we want to combine the elastic and the electrical properties. So quite similar. Of course, in practice, in resistivity, we need to put in the electrodes, which might be an effort, but afterwards the instrument is just measuring by itself, whereas in seismic, we have to have much more effort in generating the source. EM, electromagnetic induction, could help us out, because that is, we don't need any contact, no galvanic contact with the ground, which is then easy to make surveys and mapping, but the penetration depth of these standard FDEM techniques, so frequency domain electromagnetics, the penetration depth is very often very shallow, like the uppermost 6 meters or so, which means we can get the active layer, but not below. So in this example, this is a mapping of electrical conductivity. Again, at Chiltern, we see a pipe here, but we see also some parts which have a lower conductivity than others, which can be related then to active layer or to ice content. Whereas in a different site, there is no such variability. If we want to go deeper, we can use transient domain electromagnetics. So 2 coils, as transmitter and a receiver coil. And we can get soundings again of apparent resistivities, or in this case, signal strength in terms of the voltage. That can be inverted to give again electrical resistivity or even chargeability, so the part of the complex resistivity. In this case, a rock glacier, we see the base of the resistive zone here. So we see the base of the ice-rich part of the ground, which would be here 20 meters thick. So that is an alternative if we want to go, if we want to have a sounding. Again, we profit from the fact that ice has a very high electrical resistivity and the unfrozen part has a low electrical resistivity. And finally, radar is, of course, very easy to use, very quick, very doesn't need galvanic contact. So also for glaciers, obviously glaciers and snow, that's the method to use. So I guess you're all familiar with that. So if you go on a glacier, that is one tiny glacier in Germany. Even if you look at raw data, we see very often the surface and then the depth of the bedrock. We also have wave velocity, which for ice is rather homogeneous, which means we can define a depth scale very easily by converting electromagnetic wave velocity to depth. That is, for example, this example being done here, and then you can follow this bedrock topography very easily below a glacier. Now, what happens if we go to a rock glacier, permafrost, again, that example from before, we have now this rock ice mixture. So if we're lucky, we can still get the base, but we can also get a lot of in-between refractions or diffractions of the electromagnetic signal. So in a way, we have just too many reflections in our study object, which is why it's then more difficult to get a good two-dimensional result out of it. And then very often we just look at the pattern. So this pattern is quite here as well, quite indicative for bedrock, a lot of damping. Whereas if we have this stratigraphy, that would be then a talus. And if it's a rock glacier, it's probably a bit more chaotic if there's not a lot of ice in it, and so on. But very often it's really quite difficult to use radar, which is our excuse why we are not using radar so often than other disciplines. So in monitoring, what do we do? So if we have a standard monitoring station in terms of atmospheric components and let's say a borehole, then we need to make a line of electrodes, connect the cables to it, connect the instrument to it, and then we have a few options whether we leave the electrodes in place and come back 1 day later, 1 month later, 1 year later, or 10 years later, or whether we leave the cable in place. That is then difficult if the cable is quite expensive. So these typical ERT cables are around $5,000. So probably doesn't want to leave them around if there are animals or if there are instabilities. So that is when we do something which is long-term and automated. So an automated system, everything will be buried in the ground. And the only thing that you can see is then a box sticking out of the ground where everything is measured, and then maybe a solar panel putting in the energy. And this is what we are at the moment trying to develop with the colleagues in Lisbon in order to get such a system at reasonable low costs. In any case, we need the good electrical contact to the ground, which is easy if there are only stones like this or here. It's more difficult if we have conditions like here or even here, right? If this is a rock glacier and this is me trying to plant an electrode somewhere in this air, in these holes of this rock glacier. That's a bit where the experience come into play, and also patience. Can use sponges with the water, with salt water. So we tried, and also other groups tried a lot of different things. But in the end, as I said, if you leave cables around then and things are moving, then you have to accept the fact that you have to renew the setup, let's say, every few years. Nevertheless, the results are quite encouraging. So that's the operational data from Switzerland, from one of our PhD students. And this is the data, the mean data over time of different sites. So those are different places in Switzerland. And we see here a decreasing resistivity, apparent resistivity, but also inverted resistivity here. And we see also it's not trivial. It's not that it's always going down, right? So there are differences in the sites, which have to do with the difference in the material composition of the different sites. But here, that would be the raw, not the raw, that's the inverted data, 1 tomogram over 20 years, repeated almost at the same time every year. And this would be the yearly change. So if it's becoming more red, it's a decrease in resistivity over time. And this is what we then relate to ice content change. And this is what I was telling already in the very beginning, that we are now recently with the International Permafrost Association try to start a new coordinated database for these kind of surveys on permafrost worldwide. Now, what's the benefit of these automated techniques? If we don't have just one measurement every year, we can really have time series now. So that's depth here, and this is 1 year. So this is not temperature now, but this is electrical resistivity. And we see very nicely that we have this area where resistivities are lower in summer and higher in winter. We have the continuously frozen part down here, and we have the active layer part over here on the top. And this is another example from Antarctica, where the penetration depth is much lower, or was chosen to be much lower. So that works also on scales of the uppermost meter. If here the active layer is much shallower because it's much colder, which is why we see here this seasonal change, basically only in the uppermost meter. Now, looking at the time, I will hop a bit over this part if you have any questions afterwards. This is a bit the one new project where we try to see whether we can save some effort, time, and money, not doing it every year, but just going back to the same site 15 years later and see whether we get still a consistent change, which we can attribute directly to climate change or to thawing ice. As I said, I will not go into details, but these are basically, this is the reason why we want to have this database, because then we can go back 20 years later. That's this example here. If we would go, this is one part which I measured in my PhD. I went back 20 years later, and now is the question, can I relate this change in resistivity to climate change the same way as we did with this continuous measurement? So is that possible, or are there uncertainties in there? Also, only very briefly, we can, of course, do the same for seismics. And we did that for one site or for two sites in the Swiss Alps. And again, we see a clear signal in decreasing travel time, increasing travel times and decreasing seismic P-wave velocities in the same way. Okay, now to this case study in the Andes. The aim here was part of environmental impact assessment of mine activities in the Central Andes. So the mines had to do this, and then we did the geophysical surveys in order to see how much ice is actually in the mine area, because they have to prove that they're not destroying too much groundwater resources long-term wise. So I'm not going into detail whether a frozen rock glacier has any relevance for groundwater resources for the next 50 years or not. That is a very interesting debate. But geophysically speaking, it's important to know how much ice is in there in the first place. It could be a rock glacier without any ice in it, right? It could be a degraded rock glacier from where the ice has long gone. You would not see that from the surface. And that we published in two papers where most of the details are in the cryosphere, and I will show some results from there. So the data come from very different regions in the Central Andes around here. And also it's not only rock glaciers, could also be talus slopes or just colluvial slopes, just material where it's not sure how much ice is in there. And what we did is we did these electrical resistivity measurements and we did the seismic measurements, and then we combined the data, the measured electrical resistivities and the measured P-wave velocities to calculate ice content, air content, and water content on the same profile. And this is based on Archie's law, for those of you who are familiar with that. So a well-known mixing rule for electrical resistivities, independence of the resistivity of the pore water, of the porosity, and of the saturation. Then mixing rule of seismic velocities, where the slowness is averaged or weighted by the volumetric fractions of water, rock, ice, and air. So that's just weighted by the velocities of, or the velocities are weighted by the fractions. And the conditions that all these fractions, so the water content, rock content, ice content, and air content must be 1 at the end. And from these equations, if you prescribe one of these components, usually the porosity, you can calculate directly ice content, air content, and water content. Of course, Archie's law is only one possibility. You can also use Archie's law where surface conduction is included or parameterized, so not electrolytic conduction, but also surface conduction. You can use a formula where also electrical resistivities are averaged a bit in the same random way as for the seismic velocities. This would be a geometric mean, without prescribing as an Archie's law that the conducting phases are water. So that means also ice could conduct electrical current and also air could conduct electrical current, just only not a lot. But in any case, we can now, from the electrical resistivity tomogram, which you can interpret in terms of ice-rich permafrost or bedrock or active layer, together with the P-wave velocities, we can calculate now ice content, which is shown here. So this would be a modeled rocks, the bedrock, and this would be the active layer, the white part, and the blue part would be ice content. There are also examples where the ice content is 0. So where we, from the electrical resistivities, could assume there might be some ice in it. It's an elevated resistivity, but the seismic says no ice, at least not enough ice that it can be detected. So then the model does 0 ice content. And we have, as I said, we have this algorithm where we can directly from the seismic calculate where the bedrock contact is. Okay, I will hop over that. We can validate that in the Andes. We had the advantage that this is mining areas, so there are some boreholes and there are some cores which we can use to validate the data. Also, we can validate different models with different porosities or with different electrical mixing rules. And then we came up with an assessment of thickness of the ice-rich layer for the different profiles. You see it's quite a lot of profiles which we analyzed. These are all rock glaciers, these are tidal slopes, and these are colluvial sites. And we can also, at least for those sites where we have seismics, we can calculate the ice content. This is a comparison between purely remote sensing based analysis of ice content and thickness, which would be the orange estimates, and our field-based estimates, which would be the gray or the black ones here. So in this case, we found that if you use, at least in the literature, standard approaches to get thicknesses of rock glaciers and ice contents of rock glaciers from remote sensing data alone, so visually, then it's usually an overestimation of the ice content and of the thickness, at least in this study area. And the last part, which I would like to show you, is then the ground ice quantification. Now, not using these, so if I go back to this so-called four-phase model here. Here I told you we have three equations for four unknowns. The four unknowns is the water content, the rock content, the ice content, and the air content for every model cell. We have only three equations. So if we want to have a simple model, we need to prescribe one of these fractions. And usually we prescribe porosity because at least we might have a basic understanding of our field sites in terms of porosity. But obviously that is not very satisfying. And now in this so-called petrophysical joint inversion, which is this one here, we use the apparent resistivity data and the seismic travel time data and invert both together in a joint inversion directly for ice content, air content, water content, porosity, using the same petrophysical equations like here, but we try to minimize the data error directly and the model error directly in this joint inversion. We still may have some ambiguities, but we get also an estimate of porosity by this. So here we have in the inversion equation, we have then the constraint that these contents, these volumetric contents have to add up to 1, obviously, again. So the model seeks to find a model where these contents add up to 1 and are all sufficiently well matching the electrical and the seismic data. And the benefit is seen easily here. So this is one example where with the conventional four-phase model, where the rock content was prescribed, must be, in this case, constant. This is water, ice, and air, and that would be the sum. And here we have water, ice, and air, but also the rock content. So that's 1 minus porosity. And we see here the rock content, we see the heterogeneity of the bedrock in this case. Which then also should give us better estimates for ice content, air content, and water content. Problem is, I mean, the model will give us something, and we can validate probably with the ice content and water content if we have data, but usually we have no porosity data on that accuracy, which we will need. So then the question is it better to let the model decide, or to prescribe it? At least if we prescribe it, then we know what we are doing. And here we just have to believe that the joint inversion is coming up with a good estimate. But we did that, or Colleen did that in her PhD for several sites and validated that as best as possible. And the good thing is that at the end, we can come up with different ice content and ranges, obviously, for different sites, which is what the practitioners usually want to have. Again, validation data in this case is only available for ice content, which is the black line here. And then we can also see which of these petrophysical equations are matching the field data or the validation data best. Okay, this brings me to the outlook. The outlook is easy in a way that the obvious next step is use the seismic monitoring in the same way as the electrical monitoring, and then do a time-lapse petrophysical joint inversion. That has been done by a master student already, quite promising, but we have not yet really done a lot of studies on this. So we have some sites where we have the seismic monitoring, and obviously then the porosity should be the same. So we don't know the porosity, but at least it has to be constant in time, which we can put as a constraint into the time-lapse joint inversion. The other outlook is this so-called Perm2EAT project, where we developed this EAT system, which I told you already. So if you have a nice site where you want to install a permanent EAT system, you can call us. Okay, that's from my side. In summary, we think, I guess you all, I hope you all agree that geophysical techniques are useful field-based supplements to a variety of fundamental applied problems in geoscience engineering, very flexible. We can assess different physical parameters, and it's very cost-effective and logistically usually not that much demanding than a borehole or whatever. Ice content can vary strongly in time and space, so that is the main message, and this is why we need so much effort to get it. So there is usually not an easy answer to the problems. Okay, that's from my side. I hope it was not too long, and looking forward to your questions.